In this video, we'll study induced electric field. Okay, so an electric field is generated due to the time varying magnetic field. Okay, we can change the flux by various methods, by changing magnetic field, by changing area, and by changing the angle between B and A. So, uh, this unique method, by when we are changing magnetic field, an electric field is generated which is not due to the charges. Okay, the electric field is not due to the charges, it is due to the time varying magnetic field. So we can say the electric field generated is non-conservative in nature. It forms closed loop. Okay, when it is generated with the help of charges, it is conservative, but when it is generated with the help of time varying magnetic field, it is non-conservative in nature. So this is a circular region of radius r in which field is varying by some rate, let's say dB by dt, and we have to find field as a function, this electric field induced as a function of r. So let's draw a small loop inside the region. We are explaining for r less than capital R. The flux will be B into simply pi r square. So EMF induced, which is nothing but electric field induced into 2 pi r E dot dl integral, that will be dB by dt or d phi by dt, which is dB by dt because only B is changing, pi r square. From this expression, when we take 2 pi r to this side, we get E induced as pi will cancel, 1 r will cancel, so r by 2 dB by dt. This is the electric field. And what about its direction? Its direction is tangential. So let's say field is increasing, assuming B is increasing. Okay, we are assuming magnetic field is increasing with time. So the induced magnetic field will be outward. B induced must be outward. For that, the current should flow in anti-clockwise direction. So the electric field induced will be tangential but in anti-clockwise direction. So this will be the direction of electric field. These tangential directions will be the direction of electric field at any point. Okay, so this is when r is less than r, linearly increases. What about when r is greater than r? The flux can be written as, for r greater than r, flux is B into pi r square, because the flux will restricted to this region only. Okay, there is no flux outside the boundary r because there is no magnetic field over there. So it will be E into 2 pi r. This r will be small r because it is nothing but the length of the loop that we have drawn. So that will be EMF induced हमें निकालना था. So EMF induced is nothing but d phi by dt, which is E into 2 pi r, which is d phi by dt, and on differentiating this, we get pi capital R squared dB by dt. And we when take to this side, electric field comes out to be r square by 2r dB by dt. Okay, so here field is inversely proportional to r, here field is proportional to r. So if we draw its plot, it will be like this. From r equal to r, the graph is quite famous and it decreases as inversely proportional to r. So where is the maximum field? Maximum field is at the boundary r equal to r. Here at these points, field will be maximum. The field will obviously be tangential and in anti-clockwise direction if simply magnetic field is increasing. To find the direction of electric field, just assume a loop there and try to find out the direction of induced current with the help of Lange's law. The direction of induced current will give you the direction of electric field or induced electric field. Okay, now let's take a look at the next question. This is another question in which we have to prove that the component of induced electric field along the line will be same for all the points on the line. Okay, so we will be assuming 2 points, let's say point number 1 and point number 2. Okay, these will be the angles. Let's say the electric field, this is point number 1, this is point number 2. The electric field will be tangential, so their arrow should be like this. Again, assuming that magnetic field is, let's say we assume magnetic field is decreasing. In the previous, we have assumed magnetic field is increasing. In this, we are assuming it to be decreasing. So the induced magnetic field should be into the plane, be induced. For that, current should be clockwise and field should be like this, perpendicular to the position vector. Okay, this E2 and E1, these should be the fields, and this is small r2 and this is small r1. So let's draw a triangle here for better visualization. This is point 2 and this is point 1. Okay, this is at a distance r1, this is at a distance r2. These are, let's say, the angles, or just draw their arrows of electric field. This is E1 and this is E2. Okay, so we have to prove, let's say this is theta 2 and this angle is theta 1. By rule, we can say this angle is theta 1 and this is theta 2. Okay, so what about E2? E2 is nothing but R2 by 2 dV by dt, and component of E2 along line is nothing but E2 cos theta 2. So it is R2 cos theta 2 dV by dt divided by 2. So what do we mean by R2 cos theta 2? R2 cos theta 2 is d. So it is nothing but d by 2 dV by dt. Similarly, E1 will be R1 dV by dt, because point 1 is at a distance R1 from the axis. So again, component of E1 along line is E1 cos theta 1. So it will be R1 cos theta 1 by 2 dV by dt. We can say it is also d by 2 dV by dt. So again, the fields are different, but their components along the line are same, and that depends on the perpendicular distance, which is d only. So all these points, whether it is here, the field will be, let's say this is 3, the field will be E3, but the component E3 cos theta 3 will be equal to this. Okay, so hence we proved for any points on the line, the component of electric field along the line will be same. Okay, enjoy.